Namaskaram. Today we will discuss about maxima and minima of a functions of two variable. Okay, in the case of one variable calculus, we know what is a maximum and minimum of a function. In this example, these are some high points comparatively nearby points, right? That's why we say that they are relative maxima. And similarly, these are some low points comparatively nearby points. So we know they are called local minima and such things. Similar concepts, we will develop similar concepts in two variable calculus. Okay, suppose we consider a function in two variable, that means z is equal to fxy. Suppose this is the graphical representation of this function. Then it is clear that this point is comparatively high, okay, to the nearby point. So such points are called relative maximum. That is the concept of maximum. And similarly, what about this point? This point is relatively low. Okay, if you think about comparatively nearby points, so such concepts, such things are called minima. Okay, so next we will see the formal definition of these two concepts, maxima and minima of two variable function. Okay, this is the formal definition. A function fxy is said to have a relative maximum at a point x0 y0. You consider a particular point x0 y0 if there is a disk centered at x0 y0 such that, suppose you think about this point, okay, suppose this is our x0 y0, point is x0 y0, and you think about a disk nearby this point, okay, then on this disk our function value, the value at this point, the function at this point is greater than or equal to value of the function in the disk. Okay, that means f of x0 y0 is greater than or equal to f of xy for all the points xy that lies inside the disk. Okay, comparatively this value is high. That is idea. Okay, comparatively this value is high. Similarly, you can define the relative minima. What is relative minima? A function f x y. Okay, next we consider the absolute maximum. Absolute maximum is nothing. It is a maximum among it is in its domain. Okay, so a function f x y is said to have an absolute maximum at this point if f of x0 y0 is greater than or equal to f x y for all the points x y in the domain of f. Okay, so maximum among its domain. Okay, that is called among the points in the domain. That is called relative maximum, absolute maximum. Okay. Similarly, we can define our relative minima. What is relative minimum? A function f x y is said to have a relative minimum at a point. Suppose you consider this point or this. Okay, you can consider this point x0 y0, and it is clear that this is a relative minima. This is the formal definition. There exists a disk centered at this point. Yes, there is a disk like this, such that f of x0 y0 is less than or equal to f of xy for all the points xy that lies inside the disk. Clear? Then we can say that this point is comparatively minimum. That is called a relative minimum. Similarly, you can define the absolute minimum. That is nothing. It is a absolute minimum of the function in its domain. So x0 y0 is said to be absolute minimum. Or in this example, this is the absolute minimum. If f of x0 y0 is less than or equal to f of xy for all xy's in the domain of f. Here, suppose we consider the domain of f is actually this square. It's a 0, 1, 1. It's a 1 by 1 square. In this domain, this is the absolute minimum. And at this point, it has an absolute maximum, right? This is the maximum on this domain. And this one, B, is a relative maximum. And A and C, they are relative minimums. Okay, this point is absolute minimum because this is the minimum value of the function. Okay, this is the concept of relative maximum and relative minimum and absolute maximum and absolute minimum. Okay. Okay, next definition, relative extremum. If fxy has a relative maximum or relative minimum at a point, relative maximum or relative minimum at a point, then we say that f has a relative extremum at that point. So relative extremum at a point means either function has a relative maximum or relative minimum. Okay. So in this example, A, B, C all are relative extremum because at A and C has a relative minimum, at B there is a relative maximum. So such points are called relative extremum. Similarly, we can define absolute extremum. A function of xy has a absolute maximum or absolute minimum at a point, then we can say that f has absolute extremum at that point. Okay. In our previous example, yes, this point is actually absolute minimum. At this point has function as absolute maximum. So these 2 points are actually absolute extremum. Clear? Either absolute minimum or absolute maximum. Such points are called absolute extremum. Okay, next we are going to define bounded and unbounded sets in 2D and 3D space. A set of points in 2D setup is called a bounded if the entire set can be contained within some rectangle. Okay, and is called unbounded if there is no such rectangle. Clear? For example, this set is bounded because you can bound this set, this yellow shaded set, sorry, this blue shaded set. You can bound this set using this rectangle. So this is a bounded set. Actually, this is a solid in 3D. You can cover this blue solid using this cube or this box. So again, this is a bounded set in 3D. Okay, and what about this set? This set is nothing. This is our first quadrant. First quadrant in 2D. It is clear that there is no rectangle which bounds this first quadrant, or there is no rectangle which contains this first quadrant. Clear? So this set is unbounded. And similarly, my question: what about the straight line y is equal to x in 2D? Is it bounded or not? We know that straight line is like this. So does there exist a rectangle which contains the straight line? No. So this is unbounded. There is no rectangle which contains the straight line. Clear? So this is unbounded. Okay, next we are going to characterize this maxima minima in terms of mathematics. So we assume that in case of one variable calculus, suppose a function has local relative maxima or minima at a point x naught, and this suppose this function is differentiable, then we know that the tangent at this point is parallel to x-axis, right? So also we know that so its derivative or the slope of this tangent is 0. So in terms of derivative, we know that f dash of x not equal to 0, right? This is because we know that derivative is nothing, it is the slope of the tangent, and in this case this tangent is parallel to x-axis, so and its slope is 0. So that's why f dash of x not equal to 0. And we will develop analogous result in two variable calculus. Okay, suppose this point x naught y naught is a local relative maximum point. Okay, we can find the similar result in if it has a relative, if it is a relative minimum. Okay, anyway we assume that this is a relative maximum point. Okay, this is possible because we know that if x naught y naught is a relative maximum, then it satisfies this condition in nearby points. So that's why that is f of x naught y naught is greater than or equal to f of xy. Okay, that's why shape of this surface is like this at least in nearby points. Then we know, suppose our function z equal to fxy, this is the surface, z is equal to fxy. We assume that the surface is differentiable. That means suppose this function has two partial derivatives. Means fx x naught y naught and fy x naught y naught exist. In the case of one variable function, we know what is f dash of x, and that derivative equal to 0 at this point. Similarly, we assume that for this function, two partial derivatives exist at this point. Okay, then what about this value? We know geometrically what is fx x naught y naught. Geometrically, fx x naught y naught is nothing. It is the slope of the tangent at this point parallel to x-axis, right? We know that this is nothing. This is the slope of the tangent at this point parallel to x-axis. So what about the slope? Yes, its slope is 0. And similarly, what is phi of x naught y naught? Phi of x naught y naught is nothing. It is the slope of the tangent at this point parallel to y-axis. So again, its slope is also 0. So this is the one necessary condition for relative maxima. We can develop the similar results for relative minima, right? Because both the tangents are parallel to the axis. So again, the derivative is 0. So we can formally write this concept as a result. This is the result. If fxy has a relative extremum, either relative maximum or relative minimum at a point x0 y0, and if the first order partial derivatives of fxy exist at this point, then fx at this point and fy at x0 y0 both are 0. This is one necessary condition. If f has a relative extremum at a point and f has first order partial derivatives, then the derivative should be 0. Okay, and this is the geometry behind this result. Okay, we know what is a critical point in one variable calculus. Similarly, we can define the critical point in two variable function. A point x0 y0 in the domain of a function fxy is called a critical point of the function if fx first order partial derivative with respect to x at x0 y0 equal to 0 and fy means first order partial derivative with respect to y at x0 y0 that is equal to 0, or if one or both partial derivatives does not exist at this point. Okay, so either both the partial derivative exist or at least one partial derivative does not exist. That is called a critical point. Okay, actually our above result means this result is not sufficient. It's only necessary condition. If f has a relative extrema and a first order partial derivative exists, then this condition is true. But its converse is not true. That means this condition does not imply function has a relative extrema. This condition does not imply function has a relative extrema. Clear? Okay, that is the meaning of this remark. Okay, that means above result is not sufficient. That is, function of two variables need not have a relative extrema at every critical point. For example, we consider the function fxy is equal to y square minus x square. First, you have to find the critical points. So it is clear that what is first order partial derivative fx? Yeah, here fx is minus 2x, and what is fy? Fy is 2y. That means the derivative exists at all the points. So we have to find the critical point, means we have to find the points x0 y0 satisfying this condition. That is both the derivative equal to 0. So what are the critical points of this function? So fx equal to 0 means minus 2x equal to 0. This implies x equal to 0. Similarly fy equal to 0 implies 2y equal to 0. This implies y equal to 0. So there is only one point. Which point? 0, 0. 0, 0 is the only critical point of this function. Okay. Next we have to check whether yes. So at 0, 0, first order partial derivatives are 0. Clear? So we find the first order partial derivatives and equating to 0, we get a point 0, 0. That means only this point satisfies this condition. Fx and fy are 0. Okay. Next you have to check whether at this point function has a relative maxima or relative minima or not. Okay. Actually, the graph of this function is like this. This is the graph of this function. It is clear that this point is neither a relative maximum nor a relative minimum. Why? Because you think about a nearby point. You consider the nearby points for this 0, 0. In this direction, function value is greater than this point, right? But what about this direction? That means in x-axis direction. In x-axis direction, function value is less than this point. So it is clear that this point is not a relative maxima or relative minima. Clear? Such critical points are called saddle point. Okay, it is clear that at this point both the derivatives are 0. Why? In y direction, this is the tangent at this point. That's why its slope is 0. In x direction, this is the tangent at this point. That's why slope equal to 0. So 0, 0 is a critical point of this function, but not a relative extrema. Such points are called saddle point. A critical point of f of xy is said to be a saddle point if it is not an extremum. Okay. Yes, in this example, 0, 0 is a saddle point. Okay, this is your homework. Thank you.